The next talk, Tired Data Store by Sumit, Ashudeep, and Harshit, will start in like a couple of minutes.
Am I on? Hey guys, thank you for coming down for our talk. I'm pretty sure most of you might be hungry by now. We are already delayed on our talks, but we'll try to go through this quick. So as you know, the topic for the presentation here is tiered data store. This is our attempt to build a highly scalable data store, a logically single data store, which can scale across different use cases or different needs, majorly being the transactional use cases and the data, big data challenges. So that's the attempt that we are trying to do here. I have here with me Harshit and Ashudeep, who will be taking us through the entire presentation. Tier data store is an extension to the concept which Jagdish had presented during last session regarding using change propagation systems for building scalable architectures with different data use cases. We'll get started. The agenda for today would be, we'll go through the problem statement once again to understand what is the real need for having a tiered data store. How did we solutionalize for this as being the solution which can scale across all the different needs, the problem statement that we have here. We'll take you through the architecture, the different components that we have in tiered data store, how we solutionalize was for the different components. A migration, which is an important aspect because in spite of having different good solutions, if people are not able to migrate their current systems over it, the solutions most of the times are not really that useful. So we'll take you through how you can migrate over tier data store, how you can use it, and lastly the roadmap. That's what's in store for future, what we are planning to develop over it going ahead. So the problem statement. So I will take some example. I come from the eCard team, so I will take an example which is from the logistics aspects that we have faced. I'm pretty sure most of you will be able to relate to the example, given that most of you would have seen similar stuff in your applications as well. Let's say we have a logistics systems built in wherein we'll have a delivery agent who typically has a use case where he wants to update shipment data. There are different centers who want to update shipment data. These kind of use cases are more transactional data use cases wherein you want to keep on updating the transactional status updates of a shipment. You need a highly read-write heavy system plus a very low latent system. That would be a desired use case for this. So we started building this system. We had a similar system. We had an application which would be able to provide this functionality backed by a store which is a transactional store, more or less an RDBMS, which would support for these cases. Next, we were approached by our product managers to provide a new functionality for our customers who wants to see how can I track my shipment, where is my shipment, how is my shipment moving across. So for to serve these kind of use cases, what you typically need is an audit log, an audit store kind of a use case, wherein you have some granular denormalized data maintained in the system, but your transactional system typically does not need that data. It's just an audit log which you want to serve to your customers in this case. So we created a change propagation or a transformation system which can dump this data into an audit log kind of a system and which can start serving the needs of our customers here. The next, our HRs approached us and they wanted to have some data coming out from the system based on which they can make salary payouts for the delivery agents or all the agents who works in our logistics. So we now need to provide them with the productivity data. This is more or less an aggregated data over a short period of time which you want to serve out to your customer. Again, we write another transformation layer, pick out data from our transactional systems or the audit logs. We create some aggregates, we store it down in another system, and we serve it across to the HRs. So far, so good. We have 3 stores for maintaining our data, and we have some replication mechanisms or change propagation mechanisms within it, which is carrying this out. Everything being specifically written for the transformations that we need. Next comes planning. They are like, what is my resource utilization for the last 6 months? Now, to provide this data, we need to store even a larger data set, which again, we don't need in our transactional application. We don't need for the rest of the use cases that we have here, but we still need to provide this. Until we provide this data, they won't be able to plan their warehouse capacities, where should a new warehouse or a delivery center should come up, all of those, how many delivery agents do I need in a particular warehouse and stuff. So you now need to provide this aggregated data, which is more or less a medium-term data for the use cases that they have. Next comes demand shaping. who wants to go over like historical data over multiple years so that they can start doing a demand planning, start to decide where should they place their inventories, how should they place their inventories. So they want to look over an even larger data set so that they can provide this data. Again, what we did is we started picking up data from our stores, aggregated it over the years. We started maintaining it, again, a much larger set, but they could still run their analysis. And the last killer blow that we got was when legal approached us and they wanted to know data for all the shipments for, like, let's say, sent to a specific state in some specific year. Now, there are lots of regulatory requirements, government requirements, wherein you need to maintain these kind of data. Now, if you look at this data set, this is like a denormalized data set over a very large span, and you still need to maintain it, this is more like an archival store where you are maintaining all your data. So once you build all the system, want to cater to all these use cases, you have typically like a 4 or 5 data store system with multiple transformation layers which are moving across data from one layer to another, so that you can serve all these use cases. So we ended up having a pretty complex system around here, and which was like difficult to maintain. Consistency issues were there while moving across the data set. So I'm not saying that our system is actually like this, but then what I want to bring out is the complexity when you have different use cases to be served out. So the different kind of data stores that we need. To summarize what we just went across, we have a delivery agent here where the use cases were transactional. A read-heavy data set is what you need, and asset properties. Typical life cycle would be like until the shipment has been delivered. You don't need to maintain it above that, which would be, let's say, a 5 to 15 day kind of horizon. The customer use cases where, again, you need a denormalized data, but the retention would be typically a 3 to 6 months retention depending on what you want to serve back. HRs where you have aggregated data sets, again, let's say over a 3 to 6 months horizon. Planning where we already spoke a bit long term, a medium term kind of a data set, but aggregated, maybe map reduce operations should be possible on these kind of data sets. Data demand shaping, as I said, similar functionality, but on a much larger data set than what planning required. And legal, wherein again, you need a much larger data set, plus it needs to be granular, denormalized, so that you can easily pick out data and provide to the system. So these were like the different requirements that we had in our systems. We had to build for this. So to summarize the problem statement that we have, there is no store, no single store which can solve all these requirements that we had. Either you go for a single storage, your storage cost would be way too high. The performance requirements won't be achieved. Latency guarantees would not be achieved. So given all of that, and if you go with multiple data stores, as in this case we were talking about, the change propagation would be a difficult part to achieve. Real timeness would be a problem. Consistency guarantees between these different data stores would be difficult to maintain. So we wanted to basically solve for all these problems and have a single solution which is easy to be used across by different applications and served out. So given that as our problem statement, given that as the requirements, what we came out with was, this is a high-level architecture of the system that we came out with, and we'll run you through each of the components separately. But I'll primarily consider my primary data store to be a transactional store, though this can be any store which is able to give us a change event log. It need not be a transactional store always, but typically I guess 99% of the use cases will have their primary store as a transactional data store. So I'm considering that as my primary tier store here. A change propagation system which can read events in real time from the primary data store, transform over it, apply the required transformation, and then store the events in the required secondary store in the required manner. So there could be different secondary data stores, like in case of an archival use case, you have, let's say, an archival store here, you have a search index store here, an analytics store here. So this is the crux of the system that we have here. We have a global proxy on top of it, which can seamlessly talk between all these stores so that applications need not be really aware about what goes on in the background, what goes on behind the scenes. Application simply talks to the global proxy. The global proxy can take care of retrieving data from the different stores that we have behind the scenes. To take care of the storage cost and especially performance, we have a data lifecycle manager which takes care of purging out the data which is old, which is no more required in a particular data store. That can be purged out of the system. That way, you have a small data store or the required data maintained within the data store, and which takes care of the performance guarantees that we have. So this is like the high level architecture which we came across, which we built uh, for fulfilling all the requirements that we had for the problem statement at hand. And here call upon Harshit, who will start running you through the details of each of these components, how we solution for the same.
Yeah, hi. So I'll talk about what is the architecture or what is the science behind our transactional store where we want to serve our primary use case. So let's talk about the requirements. So some of these are the essential requirements that we want, and some are the critical ones. So essential ones, I would say, like it should be an asset. The scales should read out. It should be able to scale our writes. It should support our indexes, so our query are faster. It should support some kind of language which has been globally accepted. We have different languages, and they have their third-party libraries, and so this is a SQL what we it is the one which is globally accepted, which people know how to query on and how to write queries on. Then it should be highly available. There should be a way where we have a way to have a secured access to our data so that nobody else actually access those your data basically. And then some of the key requirements were like what about the failure recovery? Like you have a master and a slave replication. Your replica is not able to catch up to the master. Then there should be a way where that all the traffic should not go to that replica. It should switch to some other replica. Once that replica catches up, it should latch back to your master, and then it should start serving. So that kind of failover mechanism, failover recovery we were looking out. Then there should be a failover mechanism as well, where if your master goes down, someone should be there to take up its place and start serving your write traffic. Then once you have done that, then there's a case of data size scaling. So once you have scaled up your data store, like it will serve now 2 GB space or 10 GB space or 64 GB space, you can't scale up more as your hardware cost will keep on increasing. Then the way it has to be like you have to now scale out, you have to do sharding, you have to maintain all the partitions in that shards. So how that a single data store can do that. Then came up when you have sharded systems, then if a single shard is having so much data, how do you do a redistribution of that shard? Then came out once you have shards in place, once you have so much data in place, how you do an schema change. It should be efficient. It should it should be seamless so that you don't even feel that there's kind of slowness in the system. Then on a longer term, when you run your system for a longer time, there will be some delete query, some update query. That has created holes in your system, so you want to do a defragmentation so that you can recover that space, and basically you have gained the size which has been reduced by the fragmentation. So all these were the requirements, were the initial requirements, and then the requirements which are like, it has to be there, because these initial requirements can be served by many data stores, but then we boil down to know these are the main requirements that we want to know, as in these are the ones which will reduce that, okay, we should look out only some data stores. Then we try to explore the solutions available in the market so that we don't build it from the scratch. Then we thought of, let's say, we found like NDB is good, VoltDB is also good, then MemSQL is also good. But what we actually found is like they are kind of in-memory stores where they said, no, put more hardware, and then only you can achieve those things. Then we said, okay, we need something which can actually store data in disk rather than in memory, so that we can kind of reduce our cost on the hardware. But when we found that, we said, oh, there's no as such transactional store which can actually persist that data and have all the capabilities which we need. So then we thought, okay, these are, and also like we need something where we can actually build functionality if it's not there. So what we found is, okay, we have all the requirements, these stores are serving our requirements, but they are all closed source. So we said, no, we'll add one more requirement, that is, we need an open source solution to that. And then they came up with solution which suits our requirement and something where we can contribute back. So we said, okay, let's figure out what Vitess is serving for us. And then we looked out Vitess solution. It's a YouTube open source solution. And what we found is, yes, it is good. It has it's basically a proxy which is running on your MySQL systems, and it's basically follows a push down approach. So whatever data it comes, it don't do much science on that. It's want to send all the query to your MySQL system to do it, as it is already optimized for running all those queries in a better way. So we found that, yes, it's a good way of doing it, because you don't want to build a new data store from scratch. It should be something which is able to manage all your shards, and it should able to propagate maximum to what is already efficiently running in our current application data stores. So then we see, okay, it is good. Then it supports an application unaware sharding, so your application doesn't have to know where your query is routing to. You just send a single point of contact is for you. You just send a query. It will manage like in which shard your data is, or in other shard your data is. So it will give you all the data what you need by just a single point of contact. Then as you talked about, when you have sharding, it should be able to reshard your data once your data size is growing. So it is able to achieve that. It is able to give you a reparenting solution where your master is going down or it is slowing down. So you can always have one more replica coming in place of that master. Then a transaction management. So once you have actually sharded your solution, you can have a cross-shard transactions available. So to achieve that, they maintain a transaction with MySQL. They have I'll talk about the architecture how it is. So they have transactions be managed by each proxy which is running on MySQL, and currently they are doing it a best effort, but the 2PC or the two-phase commit is almost there. So once it is up, you don't have to worry about your cross-shard transactions as well. And then the connection pooling. So currently apps has to actually maintain all the connection count, that how many connections this app is containing, how many connections this app is creating. You don't have to worry about it. Whatever you create is a virtual connection. Actual connection to your database is managed by Vitess. Then cluster protection, it is very important. Like you sometimes run rogue queries, or you don't actually kill your transactions are on running, or you have some queries you don't want to run on your database. So, and also the access control list law, ACLs, which is provided. So these kind of cluster protection it will give you. And once you have a huge set of shards and everything, you want some UI or something that way you can actually see like what is going on, how many size I have, which master is there, how much replication lag is there. So that's a cool UI they have for the cluster management. So this is the architecture, the overview. So here you have shards, multiple shards lined up. Each will have their own master replica replication in master and application mode. Then they have VT gate, where is the global proxy. It is also horizontally scalable. You can add more and more global proxies on that, where your application will directly talk to that global proxy, and it will understand where the query has to be routed to. There's a separate index store. So so once a query is there and you have a secondary indexes on that, it will store all the indexes over here. Then you have a log server. So this is your actually a topology server where your topology is maintained by them. Then you have that UI or admin tool from where you can even run DDL so that it can seamlessly propagate to all the shards. So once we looked at their architecture, we said, yes, it can actually do something for us. And we were the early acceptors that, yes, this architecture can actually scale and we can actually work on them to do what we need. So then this is some of the contributions that we made to them, so that first one is the JDBC driver. So now your application is a drop-in replacement for your existing running MySQL instances. You can just plug in our driver on your application and you will just have a sharded solution for you. Then we added more sharding column support. So we added more sharding column support. So so currently the sharding column was only for integer based. Then we added, no, we need more. We need some people need a varchar kind of support, some need a different kind of column support. So we added, we extended their sharding column support. Then the query routing, which we did on the secondary indexes, we actually made it more efficient. We thought what kind of data we need to store in the index store so that it can have more efficiency. So we actually improved upon their query routing on the secondary indexes by storing the relevant information in their index store. Then we added more query support. We have now multi-row inserts to have better performances. We added batch query support, so you can, in a one hop, you can send all your queries to it. It will actually process it. It will understand which shard it has to go, get the results back, and then you get results back at a one network call. Then we added monitoring and alerting on them to have to using collectd, so that you can actually push to any data store where the collectd can actually push it. So we added that plugin. Then also for the backups and restore, they were backing on the file system and on their Google Cloud Storage. We added support for our own internal D42 system as well as the S3 system. Then it's not actually the bug fixes. It's more of a use cases where they thought that it won't come. Like someone said, oh, I change some table and I run a drop table and a create table. So they never thought that who will run these kind of use cases. But that kind of fixes we did. So you have a use case, we did it like that. So this is something. This is what we did for the transactional store. Then once the transactional store or the primary store is use case is full, we said, okay, we should go with it. It is serving a use case. We can always contribute back. So then we said, yes, the transaction store is done. We know now what we need, and then we say, okay, now let's move on to what we need in our change propagation system. So, so the basic requirements were that it should be fast enough, it should be reliable. Once as the shards are maintaining ordering, we also wanted that our change propagation system should also maintain an order in which it will send data to the other tiers. So that was the requirement came up. Then it should be scalable. As our QPS are scaling on our primary store, our change propagation system should be able to also scale up, and it should be highly available. It should be able to serve multiple stores. Then if some data store, the data store which is not able to keep up with the speed of the change propagation system, then there should be some mechanism where it can actually catch up with the older data and then again relay back the current events which are coming up. Then we thought, okay, what we should do. Then we said, oh, we have our ASOP. It's already a tried and tested solution in Flipkart, and it's been used outside as well. So I'll just talk you about what are the basic components of ASOP. It's more complex than what you are seeing over here. So you have a relayer in place. It is actually pulling all the event logs from your transactional store. Then you have a client cluster. It is actually you're getting receiving data from your relayer, and it is pushing the data to your secondary store. So this client cluster is highly available system. Your relayer is also highly available using behind the store. It's a zookeeper, which is from where they are all coordinating. Then if your client falls off because of it is not able to cope up with the speed, then your client can actually use the snapshotting version of it. It will actually take the snapshot from this position. It will move the data to your secondary stores, and once the snapshot is in place, it will latch back to your relayer, and it will start data flow from there. So this is about how change propagation system is working. There's much more science about it, which was actually talked in previous session as well. So next is about architecture, about the secondary tier stores. What was the requirement? What were the use cases we saw? What we want to achieve here? And I would like Ashu to actually go through this. Thank you.
Thanks, Harshit. So far we have covered transactional store, as in our primary store, the change propagation system. There are two essential components that are left behind was secondary tier stores and the data lifecycle manager. So I'll start off with the requirements and the architectures of like what we thought about what kind of secondary tier stores can be there. So if we come to the requirements, secondary tier stores can have multiple requirements. So first is you don't want to, like compromise on the SQL query set. You are okay with living that I'll use same kind of SQL queries which I'm firing on the transactional or primary store. But you're okay with compromising the cost in the sense that you won't use SSD. So okay, MySQL and MariaDB can be the solutions. We'll be using relational DB in secondary tier stores. Then comes along some kind of reporting and analytics use case, which will be running very heavy queries on these like secondary tier systems, for which like HBase suffice our requirements. There can be archival use cases wherein you want to run a query once in a while, not every time, but for reporting or some analytics. Then there are requirements like search indexing store, for which you might be using Elasticsearch or Apache Solar for as your secondary tier stores. So like what I'm trying to show off here is like basically in secondary store there are different kind of requirements that can happen as compared to primary transactional store, which is mostly a relational database. Coming with a set of requirements we had. So what we thought of that our archival tier store should be a big data store. It should be able to handle large amount of data, and that should be compressed. That should have a compressed storage system for saving costs. It should have faster lookups for reporting use cases. There should be a way that analytics queries can be run. There should be, so most of the secondary tier requirements that we have, like mostly if we go with HBase or something, those are optimized with primary key lookup. But we might be having a requirement in which secondary index-based queries can also come in. We also have to thought about how to optimize those kind of queries. We can run MR jobs for, do some kind of analysis, data mining, or built-in machine learning models for this. So these were the set of requirements that we had for archival tier. Now coming to the architecture of archival tier, what we had was a global proxy and archival layer proxy. So out of the secondary tier storage that we thought of, which I shown here, like what we have solved for now is HBase, specifically for archival storage in the secondary store. And there, like all the primary key lookups can be done directly from HBase. But we might be needing some support for secondary index-based queries. And for that, we thought that there should be an index store or Elasticsearch, which this archival layer proxy can coordinate with, and it can be able to efficiently serve the secondary index query requirements. Okay, so this was about the archival tier. Then there was another essential part of the system, which is like, let's say we have given you this data store. We have inserted the data. We have queries serving. Our traffic is being served from that. But what about the data lifecycle management? So here I would like to, before even going into a data lifecycle manager, I would like to talk about few requirements that we generally have. So let's say there is a shipment which has been delivered to the customer, and it's no more have a sort of use case of transactional storage. So we don't want to live with that kind of entity in our transactional storage, and we want that, okay, all the other kind of needs that we have for that entity, like for reporting or some analytics, should be served from archival storage. And there is when we think about that, okay, let's remove or purge this specific entity from transaction store. Whatever use cases we have will serve from the archival store. The another thing that comes in is basically in our mother hubs, if you see, so there are so many shipments, which gets lost, and sometimes erroneously people mark it as shipment has been deleted or it has been lost and state has been changed to deleted. You can safely remove it from transaction store. And after some point of time, we recognize that, okay, no, I just find it out. I just found this shipment out, and I want to run transactional use case on this entity. So at that point of time, there is another thing that comes into picture is resurrection. Now, that entity has completed life cycle. We have removed it from transactional store, but we found that entity out and we want to serve it. So basically, we know that this information will be there in archival store. So we just want to resurrect it into back to the transaction store. So I'll talk about data lifecycle manager. So as per the requirements that we have for data lifecycle manager, what we thought about is that it should be able to understand entity relationships. most of the times what happens is, using the relational databases, it's all about that one entity is being present in multiple tables. And when you want to remove the reference of that entity, you want to remove it from every table and not some particular base table. Then it should understand the data lifecycle, as in like when it needs to be removed from the transaction store. There should be consistent data purging from all data stores apart from archival, because archival can be used to serve reporting cases or the regulatory cases that we have. And of course, this is something that came up in our requirements, that we should be able to also resurrect the data from the archival store. So these were some set of requirements that we had for data lifecycle manager. So I'll talk about this thing. So when we said it should understand entity, that is table relationships. So a conventional way of doing this is application running its own deletes. But the problem is that, application has to handle all those things, that it should delete it from base table, then all the related entities table. We just thought of, if we can solve this common problem that we have, that once the reference of main entity has gone, just remove it from all other tables as well, and then abstract this logic out to the our data lifecycle manager itself. So for that, we came up with some approach that we have in this data lifecycle manager. So our data lifecycle manager understands your entity relationship. It basically asks you a configuration about different entities that are there in the system and how those entities are being related in the form of a DAG. And apart from that, you can also give information about, okay, when do I say that this specific entity has completed life cycle? So for that, you can give some status kind of columns in the base entity itself, that like when I'm done with this entity, I'll just mark the status as completed or deleted. It can be deleted safely, and you just need to do it for base entity, and automatically the references will be cleaned out. So if I check out the end of life, right? End of life in itself consists of two phases. First is detection, that basically now this entity is okay to be deleted from transactional store. I no longer need to surface it in transaction because it has completed its transactional use case. The other part that is important is what are all related entities that needs to be removed. So first thing is basically to detect that this entity has completed its life cycle. So what we came across is application just by using global proxy, some kind of give the reference that, okay, I am okay with deleting this entity based on some status, and our data lifecycle manager understand that, okay, this is the base entity that you need to check for, and it calculates all other entities for that base entity that can be deleted. So it detects that this entity has been deleted. It constructs all the related entities or all the related queries that needs to be deleted. And it does it in some manner that, when it tries to execute those deletes, those replication, because our change propagation system understand only the changes, and it can percolate all the changes to the archival store. So we need to do it in such a manner that, the data gets deleted in the transaction store, but it doesn't delete it from the archival store. So that is where some logic has been written so that all these changes are not percolated to the archival store. So that's about purging. Then, okay, so we are done with the system, like we have given you a data store, we have provided you a way to, manage data lifecycle. What's next? Is this the only thing that you need to do? So we thought, there should be some additional features as well, which would be expected from us when someone tries to onboard to our system. And for that, like a single JDBC driver has been developed, which will be interacting with the transaction store as well as with the archival store. So you don't need to, create multiple connections, handle them separately if you want to do it. It's just a JDBC driver, a single driver. That's your point of contact, which can do the transaction management in the transaction store. And if you want to read something from archival, it will do. Then, some guys have or some teams have specific use cases that I only want transaction store as of now. I don't give a damn about that. I want a secondary tier store or so. But fortunately, or unfortunately, sometimes it happens that once you try to onboard the system, after 2 or 3 months, you realize that now I need a secondary store as well. So we created our own MR application, which can at any point of time bring the secondary store. Okay, sure. Secondary store, yeah. And of course, let's say we are done with all these things. What about debugging or some issues that are coming in. So we have created some nice dashboards which will at any point of time reflect if there is something that is screwing up your transaction store or some problems with the archival store that is happening, what are the kind of queries that are the culprit for that, and based on that you can always set up alerts on it. So yeah, let's say we are done with all this. Now how to migrate this thing? Obviously new applications can very easily migrate to data store, but for already applications that are being serving live traffic and they want to migrate to tier data store because of scalability problems, what's the way for them to migrate? So these are our steps. Like you bring up Vitess on top of MySQL. Okay, Vitess like Harshit talked about. Then if you want the secondary tier store as well, just use MapReduce app to migrate data to or set up the data in secondary tier stores. Place change propagation system for real-time data movement between transactional and secondary tier. And then once you're done with all these things, initially, like when I said bring up Vitess on top of MySQL, it's an unsharded store. And then you go ahead with this thing, okay, I want to shard this transaction store as well. So these are some of the steps that people should follow to migrate to tier data store. And then there are some things in the roadmap for us that we are thinking. So it is like DDL to internal schema conversion. So one of the most common use cases is, you have the DDLs, you want to apply them on different data stores, and you want all those changes that you have applied on transaction stores should be replicated or should be applied in the secondary tier store as well. So at this point of time, when you have a single shard system, it's very easy because it's just a one MySQL instance. Here the problem comes in when you shard the system, all the changes should be applied on all the shards. So that is where comes the concept of, the DDLs that you have given and might be having some indexes as well. And when I talk about indexes, the database indexes are much different as compared to where we here also have to bring in some concept of shard indexes, which will have efficient query routing. So all that sort of conversion, DDL to internal schema conversion, is on our roadmap. Then towards transactional store side specifically, since we have, currently we were having only one single data store, now it will be sharded enough. There comes the concept of distributed transactions. So two-phase commit protocol is already almost there as a protocol, and it's been in the implementation phase. Then enriching query support, suppose you want to run analytics query or do some sort of aggregations on different shards, that we are providing. Then row caching is another important features we are trying. And then in change propagation system, ASOP, we are working on bringing a cluster management to manage all the nodes towards the archival store. Like we are building a proxy layer and Elasticsearch store for indexes. Question and answers and any feature requests that you have. Thank you. Yeah. No, that can be different. Yeah. Come again? Yes.
So actually, your initial query will be in SQL. Once it is been received at global proxy, it's no more SQL. So we interpret the SQL query, and accordingly how your data store talks to, if it's talks through JSON, we'll send it as a JSON request, and that will give you return back. And for sorry,
Joins for?
Right. Okay. Yes, so it will be like fetching data from one table and then put it in the query and then send it to the second table to get the data. That's how like your joins work on.
So joins you are saying towards transaction store?
So that's part of query planning. See, what you're talking about is query planning, right? So if that end data store does not support that kind of query, to join two tables, let's assume it's just two tables, right? You can always fetch data from one table, right? Apply the where condition on it, and then take only that data set and fetch from the second table, right? So that's the implementation. That's query planning. So SQL is just a language. What he's trying to say is, so it supports SQL, so it's easy for others. It's not necessary for the end data source to support SQL. So that query parsing and query planning can be done by the proxy layer. And it's also not complete SQL support. It can be some SQL support which we decide that is sufficient or necessary.
So the same thing that we did with the archival tier, right? The layer of archival proxy that you have, that accepts SQL, that will do the query planning, that will convert it to the H-base
Query.
concept. So it will end up then querying it over H-base based on the H-base functionality.
Like Vitess.
Did you consider Apache Calcite for the same? You call Apache Calcite, which does the same thing. What your lower top layer is doing.
So see, there are a number of projects which can do query parsing and query planning, right? So in this case, the global proxy which is there here is something which has come with Vitess.
Right.
So Vitess is a YouTube project, it has come with Vitess. So we are currently using the same thing.
I'm talking about between Vitess and archival store and other.
That we have not yet, the other archival proxy we have not yet built, and that proxy is currently being done by the JDBC driver. So it sees what kind of connection it is and sends it either to Vitess or to HBase.
We have to end the session to continue for lunch because the lunch break has been shortened. You can continue the conversation with him just after the. Thank you, guys.